Okay, geometry, we're going to move on now into section 6.4. And if you recall, section 6.2, the last one we just did, was dealing and 6.3 if we covered that too this year, dealt completely with the first special type of quadrilateral in this chapter, which was parallelograms. Now in 6.4, we move on into some different types, and you'll notice there's three in the title here, guys. We're going to be talking about rhombuses and rectangles and squares. All right, so we're just kind of attacking this one at a time, and we're going to begin talking about a rhombus. And our definition of a rhombus, everybody, this might very well be one that you guys haven't heard of before, or if you do, you kind of know what it is, but not really. Well, here we go. Our formal definition of a rhombus is a parallelogram with four congruent sides. Now, I cannot stress enough that we've got to read our definitions slowly and carefully, and we've got to think about what each word means in turn. The very first thing in this definition of a rhombus is that a rhombus is a parallelogram. And that right there, you guys, in fact, let me just box that up temporarily. A rhombus is a parallelogram. Well, guess what? That tells me five important things about a rhombus. Because a rhombus is a parallelogram, I know that everything we learned about in section 6.2 that applies to parallelograms also applies to a rhombus. Okay, for starters, by definition, the opposite sides of every parallelogram are parallel. So that means, and I'm going to erase this, guys, because it just gets too messy, the opposite sides of a rhombus are parallel as well, because a rhombus is a parallelogram. What else? Theorem 6.3. Opposite sides of a parallelogram are congruent. Well, that means opposite sides in a rhombus are congruent. Although by definition here, all of your sides are congruent. I also know, in no particular order here, that opposite angles are going to be congruent, because that's true. Oops, that's bad. Because that's true in every parallelogram. And also, oh my gosh, the diagonals bisect each other. That's a common midpoint. So that nobody's writing this down, I hope. That's congruent to that, and that is congruent to that. My gosh, that is a lot to draw in one diagram, and it's way too messy, and it's too much for anybody to be able to understand. But that's the importance, everybody, of knowing definitions and knowing important words here. A rhombus is a parallelogram. So everything we've already learned about parallelograms still applies to rhombuses. But where a rhombus goes one step further than a normal parallelogram, which we would normally draw looking something like this, what makes a rhombus unique is that it has four congruent sides. And you can see that in this diagram here by looking at the tick marks that we've drawn on all four. So basically, somebody told me this once. They said a parallelogram is basically like a rectangle that's slanty and kind of started to tip over to the side. Well, in that line of thinking, if you started with a square, which we've all known since kindergarten, and then said, okay, a rhombus then is just a slanty square, like it's kind of tipping over a little bit. And you know what? I get that. Let me just say real quickly, I bet some of you are annoyed right now at this word usage here, rhombuses. And one word that you guys are going to hear a lot out there in the world is rhombi. And some people, in fact, even me, up until recently, use the word rhombi instead of the word rhombuses to suggest more than one. Because they say, all right, a word that ends in US, when you go to make it plural, you just change that US to an I. Words like radius or cactus. And the difference here is, everybody, I just learned this myself a while ago, that trick of turning a US into an I is a trick of Latin. All right, cactus, radius, things like that. But rhombus is actually based off of a Greek root, and Greek words that end in US don't get that little plural trick. So octopus, everybody, is another word based on Greek, so the plural of octopus is octopuses, not octopi. A little fun tidbit right there. Let me get rid of a lot of this junk that's on this page right here. We really don't need much else. That's it. You guys need to know your definition of a rhombus. Moving on now, there are two properties or two theorems that go along with every rhombus. Theorem 6.13. If a parallelogram is a rhombus, then the diagonals are perpendicular. Now, this is not the case in a normal parallelogram, everybody, but if your parallelogram happens to be a rhombus, which means, and I got to try to freehand this carefully, if all four sides here are congruent, then the diagonals, that I'll draw one right here and one right here, the diagonals are going to be perpendicular to each other in a rhombus. Okay? The reason for that, everybody, you do not need to write this down. But let's think about this. We already know that this figure is a parallelogram. That means that the diagonals bisect each other. That piece is congruent to that, and this piece is congruent to this. Okay? Now, if this figure is also a rhombus, that means that all four sides have to be congruent to each other as well. So I'll do a triple tick mark on the four outer sides. And now I want you to notice that this rhombus has been cut up into four triangles. I think you can see that already. Each one of those four triangles has a side with one tick mark, a side with two tick marks, and a side with three tick marks. That means that all four triangles are congruent by side, side, side. And if all four of those triangles are congruent, then all four of these angles in the middle have to be congruent as well. We also know that those four angles together have to add up to a sum of 360 degrees. Together they make up one complete circle inside the figure. So if there's four angles in the middle of this figure, guys, that add up to 360 and they're all congruent, we would just take 360 and divide that by 4, and that would get us 90 degrees for the measure of each one of those four angles. So that, everybody, is a very informal proof that says if you're dealing with a rhombus, then your diagonals are perpendicular. Now, I'm going to attempt to show you something here, and it's probably not going to work out very well. But if I were to draw, and trust me, I'm going to erase this and not do much with it, but if I were to draw a parallelogram here that is not a rhombus, everybody, watch what happens. Let me do it this way. If I try to draw the two diagonals now inside that parallelogram, this one here and this one right about here, those two diagonals are not going to be perpendicular to each other. I think we can tell pretty plainly that this angle right here, that's not a right angle, that's obtuse. And this one right here, that's not a right angle either, that one is acute. So by drawing this really big, really wide parallelogram that isn't anywhere close to being a rhombus, you can really see that it's obvious that in most parallelograms, or I'll call them regular parallelograms, shouldn't use that word, normal parallelograms, the diagonals are not perpendicular. But in a rhombus, they are going to be. Okay, let me get rid of all of this junk and that and that. All right, and now from here, let's get rid of that. All right, guys, and let's move on to Theorem 614. Right here. And this is the second property now, the second theorem going along with a rhombus. If a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. Let's go back to the same diagram we had for just a second, and let's go ahead and name that figure A, B, C, and D. Okay? Now, because this figure is a parallelogram, we already know that opposite angles are congruent. Angle D is congruent to angle B, and likewise angle A is congruent to angle C. But for the exact same reason that we talked about in Theorem 613, the fact that the diagonals create four congruent triangles by side, 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 that now tells me something new. And let me switch colors here to try to show this, everybody. That now tells me that this angle right here must be congruent to this angle as well. And because B was congruent to D, this angle is congruent to this angle. All four of those get a single tick mark there. That means that whatever the measure of angle D was, let me just say that angle D was 80 degrees right there. Because that got cut into two congruent angles, that means that angle D got bisected. And each one of these would have to be 40 degrees all on its own. Likewise, the same thing happens over here. Let's think about it, guys. If angle D was 80 degrees, then angle C right over here which is a consecutive angle to angle D, would have to be supplementary with it. So 180 minus that 80 is going to get me 100 degrees for the measure of angle C. It then gets bisected, and each of these little angles would have to be 50 degrees. Oh boy, and now I've made it really messy, but let me focus on this triangle up here on top. And what do we think we know? Angle ABD right here is 40 degrees. Angle BAC here is 50 degrees, and we believe that we have a 90-degree angle right there. Well, guess what, guys? 40 plus 50 plus that 90, that adds up to 180 degrees, so that makes me feel pretty good then about what that one looks like. So, what have we learned here today? 3 things about a rhombus. Start with its definition. All 4 sides in a rhombus are congruent. And then because of that fact, 2 new theorems now. First, the diagonals are perpendicular in every rhombus. And second, the diagonals bisect the angles that they are drawn to in every rhombus. So, with all that in mind, everybody, let's knock out a couple of examples right here. So we'll look at this one here first. It says, find the measure of each numbered angle. Angle 1, angle 2, angle 3, and angle 4. Now you'll notice my directions don't use the magic word. My directions do not say we are dealing with a rhombus. So are we? Well, yeah, we are. And the reason why, let's go back to it, the definition of a rhombus, right here, guys, is a parallelogram with 4 congruent sides. And if we look at this figure, what can we tell from the diagram? We can tell that the big figure has 4 sides, so it's a quadrilateral. And we can see the tick marks, everybody. I don't know if you noticed them. Here, 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 and here. So any quadrilateral with 4 congruent sides must automatically be a rhombus. Now some of you are saying, wait a minute, it could be a square. Here's the fun part. A square is a type of rhombus. And we'll get to that a little bit more later on. So now that we know this is a rhombus, the definition and the 2 theorems we talked about apply. So let's get started, guys. The measure of angle 1 is right there in the middle of this figure where the 2 diagonals intersect each other. So let me go back to my notes and look for something that talks about the angles formed in the middle, and that is going to be Theorem 613. If a parallelogram is a rhombus, which this one is, then its diagonals must be perpendicular. That means, you guys, that all of these angles in the middle are right angles, including angle 1. So the measure of that would have to be 90 degrees. And that will happen in every rhombus. Let's move on to the second one, measure of angle 2. So now what's going on here? The only interesting angle measure that I know is this 58-degree angle right here. And let's think about what's going on here, guys. The second theorem we learned, Theorem 614, says if a parallelogram is a rhombus, which this one is, then the diagonal bisects a pair of opposite angles. So if you've got a 58-degree angle right here, that means you have another 58-degree angle right next to it. Now, that makes the measure of this large outer angle the sum of 58 and 58, which is 116 degrees. Because this rhombus is also a parallelogram, the opposite angle down here must be congruent to the one in the top left. This is also a 116-degree angle, and once again, this diagonal bisects that 116-degree angle, so angle 2 is going to be 58 degrees as well, just like these ones up here. So angle 2, 58 degrees. Angle 3 is going to be the same as angle 2. These guys right next to each other have to be congruent because the diagonal bisects that 116-degree angle. Okay, so that took care of the third problem. And the fourth one, measure of angle 4, well, now let's go back to what we talked about on the last slide. There's a lot of different ways you could do this, guys, but I think this is the most direct. You've got a triangle right here between the 2 half diagonals on the bottom and then the bottom side. And within that triangle, there are, of course, 3 angles, angle 1, angle 3, angle 4, and the sum of their 3 angle measures has to be 180. And since we already know the measure of angle 1 is 90 and the measure of angle 3 is 58, all we really need to do here, guys, is take 180 minus the measure of angle 1, which is 90, minus the measure of angle 3, which is 58, and I'm pretty darn sure that is going to leave us with 32 degrees left over for the measure of angle 4. Okay, and that's kind of how we attack a problem that looks something like that. Let's do another one with a rhombus here, guys. Example D. Find the measure of each numbered angle in this figure right here. All right, so what's going on here? First of all, again, the word rhombus doesn't show up in the directions, but as I look at the diagram, I've got double tick marks here, 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 and here. So even though I don't think I drew a very good diagram here, guys, I know that this figure is a rhombus. So with that in mind, it's also a parallelogram. Let's remember some things that we know. Actually, I think the easiest thing to start with here, everybody, is the measure of angle 3. Because this figure is a rhombus, it's also a parallelogram. And opposite angles in a parallelogram have to be congruent to each other. So the measure of angle 3 is going to be 130 degrees, just like the angle that's opposite from it. Now let's keep going. The next thing I would probably want to do is figure, well, there's a couple ways to do this now that I think about it. Actually, let me focus on it this way. I think this is better. If we take a look at this triangle that's here and here and here, 3 sides, everybody, just kind of highlighted that in purple. Obviously, there's 3 angles to this figure. Angle 1, angle 5, and the 130 degree angle. But ask yourself, what kind of triangle is this drawn here? And the answer is, that's an isosceles triangle because it has 2 congruent sides. And if we remember from chapter 4, everybody, if a triangle has 2 congruent sides, it also has 2 congruent angles. Angle 1 right here is going to have to be congruent to angle 5. So if I were to call that x, and look at this purple triangle, I've got an x for the measure of angle 1, another x for the measure of angle 5 since they're congruent, and a 130 degree angle for the vertex angle. The sum of those 3 has to be 180 degrees. So what now? I would subtract a 130 from both sides. Okay, that will cancel. And at the same time on the left, I'd add up x plus x to get 2x equals, and simplify the right side, we'll get a 50 there. And then we would just divide both sides by 2, pretty as you please, and get x is equal to 25. That, everybody, was the measure of angle 1. 25 degrees, and it was also right here the measure of angle 5, 25 degrees as well. And now, as I'm hoping you guys noticed, let's go back to that theorem 614 that says right here, everybody, that the diagonals of a rhombus bisect the angles that they're drawn to. So if angle 1 right here was 25 degrees, angle 2 is going to have to be 25 degrees as well, and so is angle 4 right over here. That one needs to be 25 also. That's how you handle that. The other way I was going to do it and then stop myself, if this angle right here was 130, I was going to find the measure of this angle right here. Those are consecutive angles within a parallelogram, which makes them supplementary. So 180 minus 130 leaves me a 50-degree angle for up here in the top left corner. And now, going back to Theorem 614 again, the diagonal that's drawn bisects that 50-degree angle. So angle 1 and angle 2 would have to be the same, all right? And they'd have to add up to 50. So I just would have done 50 divided by 2 to get 25 degrees for the measure of angle 1, and of course 25 degrees for the measure of angle 2, and then we could have done the same thing back over there in the bottom right corner. That would have been 50 degrees as well. to get the measure of angle 4 and 5. So there is more than one way to skin a cat, ladies and gentlemen, when it comes to finding some of these things. All right, guys, that took us through 4 slides, and that's our discussion of rhombuses. What's coming next is we're going to start talking about rectangles and squares, but I got a class starting here pretty soon, so I'm going to stop this video and we'll come back and finish the rest of that up later on today.